Good morning. We are studying Unit 2, that is Thermodynamics 2. Now, in this, we will study Clapeyron equation and Clapeyron-Clapeyron equation in its integrated form. Then, we are going to switch over to the phase rule, in which we will first study the meaning of each of the term phase, component, degree of freedom, and then we will derive that rule. Then this phase equilibria will be applied to the various one component system. In our syllabus, we are going to cover two one component systems, that is water and CO2. We will see the similarities and the differences between these two systems. Then we will apply the phase equilibria to the two component system, in which lead silver system is in the syllabus, which is known as Pattinson process. It is used for the desilverization of the lead. After that, we will see Nernst distribution law, its limitation, its applications, and the solvent extraction theory. The main objective to study this unit is a system. It consists of the parts which have different physical properties, sometimes different chemical properties also, and which are separated by boundaries. The system is said to be heterogeneous. The equilibrium between different parts, or we can call it as a different phases. There are different equilibria which exist, and these are well explained by the four principles, that is law of mass action, Clapeyron equation, phase rule, and the Nernst distribution law. So we will see all these equations, laws, and the phases. Now, we have developed convenient criteria for equilibrium, and for spontaneity, we can apply the law of thermodynamics to the problems of interest. In this chapter, we are going to deal with the changes of the phases of different component system. First, we will study one component system, and which are the transformation of concern for the chemist or the chemical engineers. Now, the two phases are at equilibrium, that as a function of pressure and temperature. Now, when we say two phases, the equation that describe equilibrium condition between the two phases of the same substance are derivable from the law of thermodynamics, and we define in that in the preceding chapter. Now let us represent the equilibrium in a closed system at any given temperature pressure. Now, as we have two phases, phase A and phase B. Now, as the system is at equilibrium at constant temperature pressure, any transfer of matter between phase A and phase B occurs with a change of 0 in the Gibbs function. That means the Gibbs function for both the phases should be same. So what is the location of the phase boundaries? So the pressure and temperature at which two phases can coexist, by making use of the fact that when the two phases are in equilibrium, the chemical potential of the two phases must be equal. That is, mu alpha is equal to mu beta. So we get this equation for the phase boundary. Now, about the slope of the phase boundary. It turns out to be simplest to discuss the phase boundaries in terms of their slope. This is Pt, that's why its slope is dp by dt. The slope of this curve will be dp by dt. Let P and T be changed, but in such a way that the two phases alpha and beta, they remain in equilibrium. The chemical potential of the phases are initially equal. The two phases are in equilibrium. They remain equal when the conditions are changed to another point on the phase boundary, where the two phases continue to be in equilibrium. At equilibrium, T, P and mu are same in two phases. When T only changes, one of the phase will disappear. When both T and P change in such a way to keep mu is equal in the two phases will continue to coexist, which are existing along this curve. This is the coexisting curve. Along the curve, potential is same, mu alpha and mu beta, these potential are same. These are two phases, suppose A, B. So chemical potential of this is mu alpha, this is mu beta, and along the curve chemical potential mu alpha is equal to mu beta. If T changes by dt, it will change, pressure will change to dP. When we change T to dt, pressure will change from P to dP. So d mu alpha means change in this is equal to change in this also, means d mu alpha is equal to d mu beta. So applying this, we know that dg is equal to vdp minus sdt. So d mu is equal to minus sm dt vm dp. So keeping this equilibrium for two phases, we can come to the conclusion that this difference in volume dP is equal to this difference in entropy dt, which can rearrange to dP by dt is equal to change in entropy to change in volume. This dP by dt, and this is nothing but our Clapeyron-Clapeyron equation. This is Clapeyron equation. In this equation, this delta S, change in entropy, change in volume. These are the entropy and volume transition. The Clapeyron equation, it is an exact expression for the slope of the phase boundary, and it is applied to any phase equilibrium of any pure substance only. It implies that we can use thermodynamic data to predict the presence of phase diagram and to understand their form. More practical application is the prediction of response of freezing and boiling point to the application of pressure. Now we will see the solid liquid boundary. This equation, we are taking only two phases alpha beta, irrespective of solid, liquid or gases. We are just considering two phases. Suppose we are considering the solid and liquid, then melting. Solid liquid phase transformation means melting, fusion. So we have to just replace this delta transition, we will use delta fusion. Delta S can be replaced by delta H by T. So we have to just consider here fusion. Fusion. The enthalpy of melting is positive, except in helium, and the volume change is usually positive and is always small. So this slope is steep and usually positive for solid liquid boundary. Now what happens with liquid vapor? Now this is liquid vapor. Liquid vapor means vaporization. So we will replace this fusion term by this vapor term. Remaining equation will be same. This vapor, enthalpy of vaporization is positive, as delta V is very very large. So dP by dt is positive, but it is much smaller than solid liquid boundary. So now we can see again solid vapor boundary also. In solid vapor boundary, we have to use sublimation term. Sublimation, because solid to vapor. Likewise, we can implement this Clapeyron equation to any phase changes for pure system. Now we will come to the Clapeyron-Clapeyron equation. What is Clapeyron-Clapeyron equation? It is given in the syllabus, the derivation. We know that dP by dt is this, and for that derivation, dP by dt is this, and then there are some mathematical steps which we have to follow. We will reach to this equation. This equation is valid for evaporation and sublimation, but not valid for transition between solid or melting of solid. It is an approximate equation because volume of the liquid, while deriving this equation, volume of the liquid has been neglected. So ideal behavior of the vapor is taken into account. However, this equation has the advantages of simplicity. So because in the calculation of dP by dt, it is necessary to know the volume of liquid and the vapor. So just for simplicity, we are using this Clapeyron-Clapeyron equation. But again, this equation is valid for evaporation and sublimation process only, where the volume of one phase can be neglected. Now we will see the integrated form of this equation. We know this equation. Now on integrating between the pressure limits and the temperature limit, we can easily reach to this equation. Here heat of vaporization is independent of the temperature. So after integrating, when we reach to this equation, it is known as integrated form of Clashes-Clapeyron equation. Now what are the application of this equation? Now its application is latent heat from vapor pressure data. Suppose vapor pressure P1 and P2 are determined at two temperature T1 and T2, then it is possible to calculate the molar or specific heat of vaporization. It is also possible to calculate delta H graphically. When we know different values of pressure against temperature, we can plot the graph and from which we can determine this delta H. Slope will be delta H by R, and keeping the value of R, we can find out the value of delta H. This equation allows us to estimate the vapor pressure at another temperature. If vapor pressure at one temperature is known, means P1, delta H, T1, T2 is known, P2 can be calculated. Simply, the equation is simple. We have 5 unknown quantities, 4 are known, then definitely fifth can be calculated. Now, what we have studied, that the temperature dependence of vapor pressure is given by Clapeyron equation, that is dP by dt is delta S by delta V. Now temperature dependence of vapor pressure of condensed phase is given by Clapeyron-Clashes equation, and this Clapeyron-Clashes is valid for solid to liquid transition. And then we have seen the integrated form of that equation. Now our next topic is phase rule. What is phase rule? Phase rule. Here we develop use of phases systematically and show how they are rich summaries of, they contain very much useful data, information about the wide range of systems. We introduce the famous phase rule, which is given by Gibbs, which shows the extent to which various parameters can be varied, yet the equilibrium is preserved. With the rule established, we see how it can be used to discuss the phase diagram that we met in the next chapter. The module introduced the system of gradually increasing complexity. We will apply that rule to the one component system, two component system, like this. So we will describe a systematic way of discussing the physical changes a mixture undergo when there is an effect of temperature, means either the system is heated or cooled, and when their composition are changed. We see how to use this to judge when the two substances are mutually soluble, miscible or not, equilibrium, when the equilibrium exists. So phase diagram are of considerable commercial and industrial importance. The mathematical basis was developed by Gibbs. Now the equation is F is equal to C minus P plus 2. F is equal to C minus P plus 2. The number of phases that can exist in equilibrium, it depends on the condition of temperature, pressure, concentration. This phase rule cannot be expressed in words. We have to express it just mathematically. What? In a heterogeneous system at equilibrium, the sum of number of degree of freedom and the number of phases is equal to the number of component plus 2. C is component, number of phases, this is degree of freedom. Now the phase rule, we will take care of each of the term. First is phases. Phases defined as it is a homogeneous part in a system, the homogeneous part which is physically and chemically different from other part, and also it is mechanically separable from other part, is known as phases. Now in the phases we will discuss some more about the phases. Pure substance. A pure substance exists, suppose solid, liquid or gas. One chemical species, pure hai. So that's why suppose oxygen, O2. benzene C6H6, ice H2O, carbon dioxide CO2, all one phase system. But this phase may be one or it can be separated to two. Mixture of gases. We know that all the gases, they mix freely to form homogeneous mixture. That's why whatever may be the number of gases in a mixture, always say that for a mixture of gases, phase is always one. For miscible liquids, suppose two liquids are completely miscible, they yield homogeneous solution, phase 1. Non-miscible liquid, when there are two liquids which are not miscible in each other, we can say phase 2. Aqueous solution, suppose NaCl, salt solution. NaCl dissolved in water, we can call it as salt solution. We know that salt completely dissolved in water, forming homogeneous mixture solution, one phase system. If we take saturated salt solution, we can see that there is some salty water and some salt, solid salt, two phase system. So likewise, we can observe easily one phase or two phase or three phase. Mixture of solid. Suppose we are taking n number of solids. All are solid. Whatever may be the chemical composition, if they are different in a chemical constituent way, then they will form a different phases. They can be easily mechanically separable. So we can generalize that whatever may be the number of gases in a gas mixture, phase is 1. If n number of components in a solid mixture, phase is n. And in liquid, depends on the solubility, whether it is miscible or not miscible. So likewise, we can determine the phase of the system, means solid, liquid, gas, or any other phase which are separable. Now come to the component. C, the term C, component. Least number of independent chemical constituent, means chemical formula. In the first look, it's very easy to understand. Water, having formula H2O, one component system. CO2, formula CO2, one component system. But to understand this, we have to again check the chemical formula of each phase. Then we have to see the chemical constituent of all the components, and we have to see whether there is any chemical formula or equilibrium exists between them, and the quantities or equations which are formed, we have to take care of that also. For example, this calcium carbonate. Now, when calcium carbonate, it is heated in a closed vessel, we get calcium carbonate giving CaOCO2. We can easily see there are three phases: CaCO3 solid, CaO solid, and CO2 gas. So there are three phases, because two solid means two phase, one gas, three. So three phases. Now we have to see what are the component. Chemically there are three different formulas. So we can say that it is three component system, but no, you are wrong. What we have to see, composition, we have to focus on the composition of the phases. Now see, suppose we select any of one composition, CaCO3, it can be represented as a mixture of two components. Choose any one component chemical constituent, it can be represented by plus or minus, simple addition or subtraction. You can get that by the addition or subtraction of two components. That means actually this system has only two components. So it is a two component system. So such care should be taken. This dissociation of ammonium chloride giving ammonia and HCl. Ammonium chloride solid and NH3 and HCl2 gases. So that means one solid, two gas, means one solid one, and whatever may be the gas, one phase. That means two phase system. Now components, we are going to see there are three components. But the system, when we write the composition, so it can be expressed as ammonium chloride, means ammonium chloride itself is able to identify, to express all the formula. So that's why it is only one component system. Thus, the number of component of a system is not only chemical entity, it is the minimum number of independent variable, independent number of chemical species which are required to express the quantities by the composition of each and every phase, either directly or in terms of any equation. So here we have to first check, what we think component is nothing but total number of constituent S, but no, we have to find out the equations and we have to subtract all such equations from that. Depending on the calculation of various number of components, in my lecture notes I have given various problems. We have taken here only 2 problems. Lot of problems are there in the notes. You can refer that. Now come to the degree of freedom. The term degree of freedom, F is equal to C minus P plus 2 in the phase rule, F. It is the least number of variable which is required to define the system completely. For example, if someone is asking address, you can tell 100 words, and a smart boy, he will just take help of 2 or 3 words and the whole address can be in that. That 2 or 3 minimum, that minimum variable which are required to define the system completely, information should be given completely. But for giving that information, for describing that system completely, whatever may be the variable, minimum variable you are requiring is known as degree of freedom. Suppose you want to plot a point on a graph. You need 2 coordinates. That means 2 variable, 2 degree of freedom. On a line, if I want to plot a point, I need only 1 variable, x variable. I can put the point on a line. 1 degree of freedom. If in a space, I want to define the system, if I want to define my position, I have to check x, y and z coordinates. That means 3 variables. So degree of freedom is 3. Whenever a system has 0 F, that means we call it as a non-variant, means 0 degree of freedom. If a system is having 1 degree of freedom, F is equal to 1, we call it as a univariant, likewise bivariant, like this. So we can calculate this freedom, degree of freedom. We can find out the number of values for P. We can find out, just as we have discussed, we can find out the values of the C. And now we can find out the values from that equation. F is equal to C minus P plus 2. Now we will derive this phase rule. F is equal to C minus P plus 2. We will derive this phase rule. Now Gibbs phase rule. Consider a heterogeneous system. A heterogeneous system of equilibrium. Components are C. Pressure concentration must be specified here. The number of variable which must be fixed in order to define the system completely. Now, on thermodynamic consideration, we will define a system in which we will take P phases. There are different P phases. And in each phase, suppose C concentration, C type of constituents, C type of various chemical entities are present. All the entities are present in all P phases. Now, suppose we have to again consider that the equilibrium exists between these, all the P phases as well as in all the chemical constituents. So, now the concentration variable depends on number of phases. In order to define the composition of each phase, we need C minus 1 constituent. There are total P phases. So what we need? P into C minus 1. This we need P into C minus 1 to specify the concentration of C minus 1 constituent in all the P phases. We take 2 as pressure and temperature. So the total number of variable for this system right now is P C minus 1 plus 2. These are the total number of variable. But do we need all the variables? No. What we need only minimum number of variables for degree of freedom. So if there is any dependent equations, dependent quantity, dependent knowledge which can be derived from this, we have to subtract it. We will see how many equations or equilibrium exist. Because whatever may be the equation or equilibrium, if that is subtracted, then this will be the minimum. This number is at present total. Now the total number of equation. Now about the equations, phase P. So total, suppose there are two phases, one equilibrium exists. Just we have seen mu of alpha, equilibrium mu of beta. Two phases, one equilibrium. So if there are P phases, we have P minus 1 equilibrium. Such P minus 1 equilibrium will exist for all the components, all C12, C, whatever may be the constituents. All such P minus 1 equation will exist for all C. So that means total C into P minus 1. These are the equilibrium which exist. So now this equilibrium, these equations should be subtracted from the total number of variable. When it is subtracted, we get this. And this is the minimum number of variable which are defining the system completely. That's why we call it as a F, that is degree of freedom. And this rule is derived by Gibbs, known as Gibbs phase rule. It is Gibbs phase rule. The maximum number of degree of freedom that a system can have, it is given when there is only one phase. If P is 1, then this one. For water, suppose C is 1, P is 1, then F is equal to only 2. That means we can plot this system on a plain paper. Because for water, C is 1. So, where to plot? If degree of freedom is 1, we can plot on a line. If degree of freedom is 2, we can plot on a graph. If degree of freedom is 3, we have to plot in a space. If degree of freedom is 4, we have to see the graph having 4 variables. Or else what we do? We assume 1 or 2 composition, some variables as a constant, and then we define the system. We will see that also. When F is 0, system is non-variant. Non-variant means the system has fixed parameters of temperature and pressure. When system has fixed parameters of temperature or pressure, that means no variable. Point. We call it as a point. That means a point has 0 degree of freedom. Curve has 1 degree of freedom. Area has 2 degree of freedom, and like this. Now, we will see that a system is in equilibrium when its property like temperature, composition, they do not undergo any change. That means it is in equilibrium. There can be different equilibrium. True equilibrium or metastable equilibrium. What is true equilibrium? If the same state can be achieved by approach from either direction. Equilibrium, true equilibrium. But metastable, if the state can be attained only from one direction and it's by very careful change of condition. Metastable, not very stable. Metastable. Now what are the criteria for phase equilibrium? There can be different criteria. Thermal equilibrium. Thermal equilibrium means we know temperature. Means temperature of the system in every part must be same. Otherwise heat may flow. So we have to keep temperature constant. Now mechanical equilibrium. In mechanical equilibrium, a small amount of matter flow if from phase A to B, then the volume of phase A decrease by small volume and volume of B will increase by small volume dV, like this. But the pressure of the two phases PA and PB, so these should be same. So that's why whatever may be the total change in volume, that will be 0. Total change in pressure, that will be 0. So mechanic equilibrium means Pa is equal to Pb. Now the chemical equilibrium. At equilibrium, chemical potential of any constituent, it must be same. We have seen that mu alpha, mu beta. Thermodynamic criteria of equilibrium, mu alpha, mu beta. Number of chemical constituent or chemical mu, chemical constituent. This mu, it should be same throughout the phase. Now we will see the general discussion about the phase diagram when applied to the one component system. In detail we will see in the next talk, but some points which I will like to focus, you just go through it. One component system, for example water. Now when a component is 1, the rule becomes F is equal to 3 minus P. Whatever may be the system, minimum one phase will surely exist in equilibrium. One phase should exist in the system. So if I take C as 1, as it is one component system, P as 1, I get F is equal to 2. 2 means pressure and temperature. So I can plot phase diagram for water or any one component system as a graph between pressure and temperature. When these two phases exist in equilibrium, then at that time F will be equal to 1. 1 degree of freedom, and we will reach to the curve. The curves which separate the three phases. There are different areas in the phase diagram which represent the solid phase, liquid phase, gas phase, single phase area. So we need a minimum 2 degree of freedom, pressure and temperature. If we want to specify any point here, we want both pressure and temperature. That means 2 degree of freedom. And along curve we need only one. If we know the value of pressure, surely we know the value of temperature. And the point O, that is a point which is having fixed pressure and fixed temperature. So that's why we don't need any more degree of freedom, because with change in pressure, temperature, this will not happen for this point. This is fixed, having fixed pressure and temperature. That's why it is non-variant. It has 0 degree of freedom. So like this, we have to define the system. Now, lowering the temperature. If we want to lower the temperature, we will go from one phase region to second phase region, from liquid to vapor, solid. It depends on where we are considering the system. So experimental procedure. How to construct this phase diagram? Detecting a phase change, it is not always as simple. We can see water is boiling. No special technique or precaution is taken. But for following this, there are two techniques. Thermal analysis, which takes advantage of the effect of enthalpy change during the transition, and the differential scanning calorimetry. Now in thermal analysis, what we do in thermal analysis? A sample is taken which is allowed to cool. This is allowed to cool means we are checking the temperature against time, not the pressure. We are taking at constant pressure. We are decreasing the temperature, not forcefully, automatically. So it will be against time, whatever may be the time required, and the decrease in the temperature. And we have to keep a watch on the slope of the line. A sample is allowed to cool and its temperature is monitored. Heat is evolved and a step comes when the cooling stops. Until all this phase transition takes place here. We can call it, if it is liquid, we can call it as that it has been solidified. So we get the cooling curve like this. C, D, E. After again decreasing, again we can see the curve like this. This is a cooling curve, curve CDE. CDE. Now, in the modern technique, more sophisticated instruments are used that we have seen. It is a differential scanning calorimetry or some ultra high pressure technique can be used as shown in the figure. On phase transition, it deals with the system at very high pressure and more sophisticated procedure has been adopted. Some of the highest pressure currently attained are produced in a diamond anvil cell shown in figure. The sample is placed in a minute cavity between the two diamonds and the pressure is exerted by turning the screw. The advance is it is quite remarkable for with a turn of screw pressure of up to 1 MBAR can be reached. So the pressure is monitored spectroscopically and here we can successfully find out the phase changes. This is the more sophisticated technique. This technique we can use in our lab also. Now the same thing for two component system. When we come to the two component system, C is 2. Minimum phase which will exist is 1. So when we calculate F, we come that here degree of freedom means we have to put C as a 2 and P is 1. So here we see that in phase rule degree of freedom comes as a 3. So it's very hard how to find out how to plot the phase diagram for a two component system on a paper, because paper allows us to plot the graph of two component system, two variable only. Now we need 3 variable, so either the graph should be plotted by computer or for paper if you want to plot we have to assume that pressure or some temperature, that C minus P plus 2 in that phase rule we have to keep that one either pressure or temperature constant. For convenience in our lab condition, in our atmospheric pressure we keep pressure constant and we check the effect of temperature. So that's why that phase rule F is equal to C minus P plus 2 is now reduced to F is equal to C minus P plus 1. One component is kept constant so that we can plot this two component system on a simple paper. That's why this is known as reduced phase rule. Now we will apply this phase rule for different systems in our next talk, that is we have to apply the system in a different one component system which we will do in the next lecture. Thank you.